A particle starts at this point A and travels along this curved path to arrive at this point B. Why does it do that? Well, because some forces act on the particle. If no forces acted on it, it would maintain its state of rest or uniform motion. This is clearly not uniform motion, so it's moving under the action of some forces. But that's not our concern today. The distance that the particle traveled is the length of this curved path, but we ask the question, what is the displacement of the particle? Now, the definition of displacement is change in position. The particle started at point A and arrived at point B, so the change in the position is from A to B. So when you talk about the displacement, you don't care about what happened in between or how far it traveled. You simply care about what was the net change in the position. We represent this change by an arrow. The tail of the arrow is at the starting point of the displacement, and the tip of the arrow is at the ending point. As you can see, this arrow, which represents the displacement, has a certain direction and it has a certain length. The length is the distance of the ending point from the starting point, and this displacement is an example of a vector. Let's give this vector a name. Let's call it A. Usually A, B, X, Y, these things represent numbers. In order to indicate that this is a vector, we put a small arrow on top. Notice the arrow does not have to point in the direction of the vector. This is how we write down with a vector. Let us now examine the properties of the displacement vector. In fact, all vectors behave exactly like the displacement vector. You will understand that by and by, but first let us understand displacement. Supposing I ask you to take your notebook and displace it by 1 meter north. That means the final position should be 1 meter north of the initial position. So we represent the displacement by a vector or an arrow pointing to the north and has a length of 1 meter. So notice it has two properties, a magnitude or length and a direction. Of course, you need not have taken the notebook along the straight line path. You could have, but you could have also taken it along some curvy path. The displacement would be exactly the same, because the displacement is simply the change in the position. Let me get rid of this curvy path. In fact, if you were sufficiently enterprising, you could have probably gone to the edge of the galaxy and come back. The displacement would still be the same. Suppose now we ask your friend, who happens to be nearby, to displace her notebook also by 1 meter north. Let's say here is the notebook, and you ask your friend to displace her by 1 meter north, in which case the notebook has to be moved from here to that point 1 meter north of the starting position along any curved path or along the straight line path. It doesn't matter. The important thing is this is also 1 meter north. So these two displacements are identical, even though the starting points are different and the ending points are different. That is because displacement refers not to the positions but the change in the position, in both cases, the change in the position was 1 meter north. Another way of looking at it is, I can take a vector and slide it anywhere without changing direction and magnitude. It remains the same vector. Let me clear some of this board and give you another example. Here I have another vector pointing in some direction. I'm going to select this vector as follows, and I'm going to move it around as follows. When I move it around like this, when I'm sliding it around so that neither the magnitude nor the direction changes, that is called translation. So when you translate a vector, it remains the same. Let's say we have two vectors. I have, all right, I'll call this vector C. Remember, I need to put a small arrow on top. And I have another vector, let's say vector D. And we are asked to find the angle between the two vectors. Very simple. I just need to slide vector D until the tails touch each other. So instead of sliding it, I'm going to draw vector D here. Watch. I draw a vector in the same direction as D and with the same magnitude. So this is also vector D, and I just need to find the angle between the two. So in order to find the angle between two vectors, place them tail to tail and find the angle. Let's get back to our object which performed the displacement A. Having arrived at A, supposing our particle or object or whatever performs a second displacement by going along this complicated curvy path and arriving at point C, we ask again, what is the second displacement? And that's very easy. The second displacement is the arrow starting at B and ending at C. So we draw this arrow. Let's give this displacement a name. Let's call this displacement B. So we have the particle starting at A, arriving at B, thereby performing a displacement A, followed by a second displacement B. Now if I look at the entire motion of the particle going through this long curved path to B and all the way to C, we can ask what is the net displacement of the particle, and the answer is it started here and ended there, and that is the net displacement when it went from A to C. Let's give this displacement a name. We'll call it C. Now we are in a position to start writing equations. So we can say displacement A followed by displacement B has the same effect on the object as one single displacement C. You could either take the object from A to B through some path, from B to C from some other path, or you could take it directly to C by yet another path. It doesn't matter. The net displacement or the change in the position is from A to C, and that is vector C. So now I need a symbol for displacement A followed by displacement B. Now this symbol can be anything. We can choose a star, or we can even choose to put a smiley face. Symbols are invented by us. But our forefathers chose not to put a smiley face there, but they chose to use the symbol plus. The plus here represents displacement A followed by displacement B. So the plus does not stand for the usual plus. For example, 7 plus 5 is equal to 12. This does not stand for the usual plus. In fact, if the first displacement A were 7 meters long, that's the magnitude of displacement A, and let's say the displacement B is 5 units long, 5 meters long, displacement C is definitely not 12 meters long. So you have to understand the plus here does not stand for our usual plus. It stands for a particular operation, which is place the first vector, from the tip of the first vector draw the second vector, join the tail of the first vector to the tip of the second vector, and that is the sum of the two vectors. So C is in fact vector sum of A and B. So even though we use the ordinary plus here, in the context of vectors, it stands for vector sum. And what is the vector sum? I will illustrate that with another example. Let us start with two vectors, vector A, and I am going to draw another vector B in some random direction. I will call this vector B. Now, I want to emphasize one important point, which is whether we have velocity, which is a vector, or accelerations, which are vectors, forces, which are vectors, or displacements, when it comes to adding vectors, we perform exactly the same thing that we do with displacements. So let's continue with displacements for now. So this is vector A and this is vector B, and we are told to find A plus B. Let us say the length of A is 27 meters and length of B is, let us say, 20 meters. Please understand the length of A plus B is not 47 meters because this plus does not stand for ordinary plus. So what does the plus stand for? What the plus stands for is the following. Think of A as a displacement, which means you start at its tail and arrive at the tip. Having arrived at the tip, now perform displacement B. So what do? From the tip of A, draw vector B. In other words, draw a vector which is in the same direction as B and has the same magnitude. If these two have the same direction and the same magnitude, they are the same vector, so this is vector B. So we have performed displacement A followed by displacement B, and now the sum of the two, this is the net result of performing these two displacements, is this one single displacement which I am going to draw in a different color. This is the sum of the two, and this vector is A plus B. So once again, how do you add two vectors? You are given displacement A and you are given displacement B. What do? You slide one vector until the tail is touching the tip of the first vector, join the tail of the first vector to the tip of the second vector. This is the process of performing addition of vectors. When do we add displacements? When one displacement is followed by another displacement. When do we add force vectors? When do we add velocity vectors? I will be explaining that in a future video. Let's start with a coordinate system. Let me draw the y-axis and then the x-axis. This is the x-axis and this is the y-axis, and let us say the first vector I am going to draw goes from the point 0, 0, the origin, to the point, let us say 1, 2, 3, 1, 2, 3, 2. So I'm going to draw the vector. The vector goes from 0, 0 to the point 3, 2. I'm going to draw another vector now. This is 3, this is 4, this is 5, that is 6, and that was 2, and that is 3, that is 4. I'm going to draw another vector now. Starting at this point, I'm going to call this point, what is it? It's 2, 0. From 2, 0 to 5, 2. Right? 5, 2. That is this point. So I'm going to draw a vector from 2, 0 to 5, 2. And I have a question for you. Are these two vectors identical? I would like you to pause the video and think about this. The answer, of course, is yes. Why? Look at this vector. It went from 0, 0 to 3, 2. That means I moved 3 units to the right. And then, I'll draw this in green. I moved 3 units to the right and then moved 2 units up. And this second vector, I started at 2, 0. 2 plus 3 is 5. Again, I moved 3 units to the right and then moved 2 units up, thereby performing the same displacement. So if I were to call this vector V, this vector is also V.